Fluids under pressure perform many valuable functions in industrial applications. For example, turbines are powered by steam that's under tremendous pressure, and gases under pressure are used for welding. But if pressure becomes too great, it can cause damage and injuries. To prevent such problems, a fluid system must have a means for relieving excess pressure quickly and safely. Various devices are used for this purpose. Rupture discs are often used in systems where problems with excess pressure are relatively unlikely. Relief valves, which open gradually, are primarily used in systems that handle pressurized liquids. In gas or steam systems, however, safety valves are used. They're able to quickly let out large volumes of gas or steam to relieve excess pressure in the systems. Safety valves are commonly used on gas or steam lines because the volume of the gas or steam increases as pressure decreases, and a gas that's under pressure may expand to a tremendous volume when the pressure is relieved. One thing all safety valves have in common is that they open wide very quickly and stay open until the system pressure drops a predetermined amount below the point at which the valve is set to open. The valve allows a large volume of gas to escape as pressure is reduced. In this part, we'll look at a Hudling chamber safety valve. This type of safety valve is named for a small space called a Hudling chamber that's located just below the valve's disc. The valve has an adjusting ring that's used to direct escaping steam either toward or away from the disc. The valve body directs the flow of pressurized fluid. The disc and seat seal the system closed under normal pressure. The disc is mounted on a stem. A spring holds the disc in place, and the valve stem transfers tension from the spring to the disc. The release lever is used to trigger the valve manually while the system is operating to make sure that the valve works properly. The disc has a lip or shoulder that isn't exposed to system pressure when the valve is closed. The lip of the disc sits above the Hudling chamber. The center portion of the disc, which is located over the valve's inlet, is always exposed to system pressure. The purpose of the Hudling chamber is to help expose a greater area of the disc to escaping fluid when the valve opens slightly. The fluid pressure acting on the increased area gives a greater total lifting pressure against the spring. The pressure at which the valve's disc begins to lift off the seat is called the valve's set pressure. The pressure at which the valve actually pops open is the popping pressure. In most cases, simmering occurs briefly before a safety valve opens fully. During simmering, the disc is only slightly lifted and the valve discharges a small amount of fluid. Simmering lasts for only a fraction of a second until system pressure acts on the lip of the disc. As the disc lifts, the lip of the disc is suddenly exposed to system pressure. Since a larger area of the disc is now exposed to the pressure in the system, more force is being exerted on the bottom of the disc. This increased force overcomes the spring tension and causes the disc to pop open to about a 60% open position. When the valve's popping pressure is reached, the valve should open with a clean and sudden pop. If the pressure in the system continues to increase, the velocity of the escaping fluid will also increase, causing the disc to gradually lift higher until it reaches the fully open position. Since the initial opening of the safety valve is about 60%, a large volume of fluid is allowed to escape quickly. After the excess pressure in the system has been relieved, the system pressure will begin to drop. As pressure decreases, the velocity of the escaping fluid also decreases. Spring tension begins to take over, pushing the disc down. The spring tension in a safety valve is preset, and it must be correct for the valve to operate properly. When the system pressure drops to the point where the valve popped open, 1,000 psi in this case, the valve doesn't close, because the lip of the disc is still exposed to the pressure and velocity of the escaping fluid. When the system pressure drops to a predetermined value below the valve's popping pressure, the disc drops down on the seat, closing the valve. This predetermined value is the valve's reseating pressure. Typically, as the force of the escaping steam is lost, the valve shuts suddenly. A small cushion of steam trapped in the huddling chamber keeps the disc in the seat from slamming together hard enough to be damaged as the valve snaps shut. When the disc is firmly in place against its seat, the valve is said to have positive seating. Positive seating is important because it keeps the valve from leaking fluid through the disc and seat. The distance that a valve disc moves from the closed position to the fully open position is referred to as the valve's lift or travel. Adequate blowdown helps prevent a condition called chattering. You see, if there's no difference between a valve's popping pressure and its seating pressure, the valve disc will jump up and down on its seat until pressure either increases enough to pop the valve open again or decreases enough to keep it closed. This condition is called chattering because of the sound that the disc makes as it moves up and down. Chattering can seriously damage both the disc and the seat because it promotes steam cutting. Steam cutting occurs when the velocity and the temperature of the escaping steam are so high that the steam cuts into the metal of the valve's disc or seat. Blowdown can be adjusted by changing the setting of the valve's adjusting ring. You see, the position of the disc in a safety valve is determined by the amount of system pressure and the angle and velocity of the steam striking the disc. When the adjusting ring is in the raised position, the escaping steam is directed right at the disc. The velocity of the escaping steam exerts a great deal of upward force because most of the steam is aimed to strike the disc closer to a 90-degree angle. In turn, the system pressure must drop well below the popping pressure of the valve before the spring can force the disc back onto its seat. So, raising the adjusting ring increases the blowdown of the valve. If the adjusting ring is lowered, it's easier for the steam to escape to the side of the disc, so much less escaping steam strikes the disc on its way to the valve outlet. The velocity of the steam exerts less upward force on the disc, and more system pressure is required to hold the disc open. So with the adjusting ring in the lowered position, the valve closes against higher system pressure than it did when the ring was raised. Lowering the adjusting ring, then, decreases the blowdown of the valve. In this part, we'll examine the components and operation of two specialized types of relief valves that may either function as safety valves or assist safety valves in protecting pressurized systems. The two types are safety relief valves and pilot-actuated relief valves. We'll begin with safety relief valves. While safety valves typically discharge gases or vapors, safety relief valves discharge gas, vapor, steam, or liquid to prevent a predetermined safe pressure from being exceeded. Safety relief valves are commonly used in refineries, on systems that contain liquid vapor mixtures, and in some low-pressure steam systems. Some types of safety relief valves are suitable for use as either a safety valve or a relief valve, depending on the application. For instance, certain safety relief valves can be used as safety valves on air systems and as relief valves on liquid systems. This is a cutaway illustration of one type of safety relief valve that's specifically designed for use in gas or steam systems. It has a long nozzle-shaped inlet, a disc and seat, a reaction hood for directing the flow of fluid through the valve, and a single adjusting ring for changing blowdown. The pressure of fluid directed against the disc lifts the disc off the seat. While the valve briefly simmers, the flow of the fluid as it discharges outside the valve's seating area increases the lifting force. Then, the reaction hood deflects the discharging fluid downward. Creating a reactive force by deflecting the flow of the fluid further increases the lifting force and causes the valve to pop open. As system pressure returns to normal, the valve closes. This is a pilot-actuated relief valve. It may also be referred to by any of these other names. Pilot-actuated relief valves operate much like safety valves. That is, they pop open rather than open gradually, and they have a predetermined amount of blowdown to prevent chattering. However, a pilot-actuated relief valve also has a separate pilot device that senses excess pressure conditions and causes the valve to open. This arrangement allows excess pressure to be detected in one part of a system, such as a steam line, while the valve protects another part of the system, such as the boiler. Pilot-actuated relief valves are often used on gas and steam systems that also use safety valves. In such cases, the pilot-actuated relief valves are set to open at lower system pressures than the safety valves are. This arrangement saves wear and tear on the safety valves and prevents costly shutdowns that would be required for safety valve repairs. You see, by law, safety valves can't be isolated from the systems that they protect because of the damage that could occur if the systems were operated without protection. So, whenever a safety valve is damaged, its system must be shut down while repairs are made. Pilot-actuated relief valves, however, can be isolated from a system because they're not a primary part of the system's safeguards. So, the pilot-actuated relief valves can be used and then repaired if necessary without having to shut down the system. The disc opens downward, allowing the steam to escape through the outlet at the upper part of the valve body. Also, in this example, the spring is placed below the disc. The valve also has a disc guide, which is a sleeve that aligns the disc with the seat. A small opening between the disc guide and the disc allows system fluid to pass through from the inlet to the bottom of the main disc. Consequently, system pressure is exerted on both the top and the bottom of the disc during normal system operation. Spring tension is also exerted on the bottom of the disc. If system pressure increases, it increases on both sides of the disc, but the valve won't open because the pressure on the top of the disc counterbalances the pressure on the bottom, and spring tension holds the valve closed. The pilot device initiates the valve's opening. The device is set to open at a predetermined pressure. A pressure-sensing tube in the pilot device detects increases in system pressure, and when system pressure reaches the predetermined level, the pressure-sensing tube activates an electrical relay. The electrical relay closes an electrical circuit and energizes a solenoid. The solenoid then lifts a pilot valve, and the excess pressure is relieved. The excess pressure that's relieved by the pilot valve comes from below the disc in the main valve. The amount of pressure that the pilot valve is capable of relieving is greater than the amount that could leak between the disc and the disc guide. When this pressure is relieved, the only pressure that remains on the disc is the pressure that's above it. With no counterbalancing pressure below the disc, the pressure above the disc easily overcomes the spring tension, so the valve opens to release system fluid through the outlet above the disc. When system pressure returns to normal, the pilot valve closes. Pressure then builds up again below the main valve disc and helps the spring hold the disc closed. External inspections of safety valves are conducted when a problem is suspected, and also when routine preventive maintenance or testing is scheduled. In this part, we'll see a typical external inspection, and we'll look at hand lifting a valve when the external inspection indicates that certain problems may be present. In preparation for an external inspection, check the operating history of the valve. This will give you an idea of specific problems that you should watch out for during the inspection. Next, proceed with a step-by-step external examination of the different parts of the valve. For this 2-ring Hudling chamber safety valve, first check the lock wire on the adjusting ring pins. The lock wire is fastened in place with a metal clip as the final step in the valve reassembly procedure. So the presence of the metal clip is a sign that the adjusting rings should still be properly set for operation. If the metal clip is missing, or if the lock wire has been tampered with, the valve set points may not be correct. Then you must have the valve taken to the shop to check the adjusting ring positions, and if necessary, reset them. Check for signs of leakage or leak-through at the discharge piping bolts and possibly around the yoke or bonnet bolts. Some valves have a yoke and a bonnet that are two connected pieces. Others, like this one, have a single piece that may be called either a yoke or a bonnet. For consistency, we'll use the term yoke. Also inspect the top or cap of the valve. Next, look for steam or warm condensate leakage around the drain plug and around the bolts on the yoke. Check the temperatures of the valve and the discharge piping. Another way to detect leakage is to check the exhaust pipe from the valve. When you make this check, be very careful not to place any part of your body over the exhaust path from the valve. If the valve were to lift unexpectedly, you could be severely injured. If steam is being discharged from the exhaust pipe, the valve is definitely leaking. An external inspection may reveal that a valve is leaking between the disc and the seat. This could occur if the valve didn't reseat correctly after the last time that it popped. Or it could be caused by foreign matter, such as ash, dirt, or rust particles trapped between the seat and the disc. In many cases, you can correct either of these two causes of leakage by manually lifting or hand lifting the valve. Hand lifting clears foreign matter out of the valve and gives the disc a chance to reseat properly. But any time a safety valve is lifted, there's a corresponding drop in system pressure. So before you hand lift a valve, notify the appropriate operating personnel so that they can compensate for the drop in system pressure and keep it from interfering with normal operations. If operating personnel aren't forewarned, when pressure drops as you hand lift the valve, they might take emergency measures to raise pressure or to shut down the system. Such actions could be costly and perhaps dangerous. Likewise, before hand lifting a valve, you must take appropriate personal safety precautions. Attaching a hook to the valve's release lever enables you to position yourself as far away from the valve as possible. This is important because when you hand lift the valve, a great deal of hot, pressurized fluid could be released. To lift the valve, pull the hook hard enough to open the valve all the way. You should hold the valve open for only 2 or 3 seconds. If you hold it open any longer, the disc could be damaged by the rush of steam. After the valve closes, repeat the inspection procedure to check for leaks and more heat than would normally be expected after hand lifting. If the valve seats properly after lifting, it should start to cool down immediately. If the second inspection indicates that the problem wasn't solved by hand lifting the valve, or if hand lifting wasn't a possible solution for the initial problem, you'll need to follow your plant procedures to have the valve examined and the problem corrected. If an external inspection of a safety valve reveals problems, you'll usually need to disassemble the valve and inspect its internal components. You'll need to follow your facility's procedures and the manufacturer's instructions for the exact steps to disassemble the specific valve that you're working on. But there are some general procedures that apply to most types of safety valves. We'll look at typical procedures for the disassembly and inspection of a 2-ring Hudling chamber safety valve that has been removed from service and taken to a shop for repairs. First, prepare the work area. Gather all the necessary tools and check the valve's nameplate data so you can locate reference material and order new parts. Clean the outside surfaces of the valve. Cleaning makes the valve easier to handle. It also prevents dirt and corrosion particles on the outside of the valve from getting inside when the valve is taken apart. To begin disassembling the valve, you must remove the release lever assembly. First, take out the cotter pin that locks the pivot pin in place. Then pull the pivot pin out. As each part is removed, set it aside in a safe place so it won't get damaged. Next, take off the release lever and then the cap that protects the top of the stem from getting dirty or being bent. Then, break the lifting nut and the lock nut free. Turn them off the stem and set them aside. The next part to be removed is the compression screw. The compression screw is precisely adjusted to maintain the exact amount of tension on the valve spring that's needed for the valve to function correctly. For this reason, you should carefully measure the screw's position. Write the measurement down so you can refer to it later when you reassemble the valve and must return the screw to its original position. Now break free the lock nut that holds the compression screw in place and turn the nut to back it out of the yoke. Then lift the lock nut and the compression screw off the stem and set these parts aside. First, break the yoke nuts free and remove the nuts from their studs. Then lift the yoke off the valve body. Handle the yoke carefully so that it doesn't bang against the studs or the stem and perhaps damage them. Remove the spring and the spring washers from the yoke and set them aside. The next parts to be removed are the stem and the disc. In this case, the two parts are connected, so they're removed together as a unit. Lift the parts straight up out of the valve body to prevent the disc from banging against the sides of the casing and being damaged. Separate the parts by unscrewing the disc from the stem. Set the disc aside carefully, with its seating surface up so it isn't damaged by contacting the surface of the work table. Place the stem on V-blocks to protect it from being dropped or otherwise damaged. Now you can remove the upper and lower adjusting rings. The positions of the rings are critical to proper valve function, so you must take measurements to record their exact locations. Measure and record the position of the upper ring first. Then cut and remove the locking wire that's on the upper and lower ring locking pins. The locking pins fit into notches in the upper and lower adjusting rings. Break the upper locking pin free and remove it from the valve body. Then unscrew the upper adjusting ring and set it aside. Now repeat these steps to remove the locking pin for the lower adjusting ring and measure the exact position of the ring. Insert a screwdriver through the lower locking pin hole and unscrew the ring by turning each notch past the pinhole until the ring is flush against the rigid rule that was placed on the valve seat to take the measurement. Count each notch as it moves past the pinhole while the ring turns. Write down the total number of notches that you counted. This number will be used to install the ring correctly when the valve is reassembled. Remove the rule and unscrew the lower ring until it disengages from the threads on the valve body. Then set the ring aside. Finally, follow your facility's procedures or the valve manufacturer's recommendations to clean all the disassembled parts. We'll look at the disc first. Check it carefully for cracks. Even the smallest crack can rapidly become large enough to allow a valve to leak. A disc that's cracked must be replaced. Dye penetrant testing is one way to locate surface cracks and flaws in the disc and other valve parts. To do this, first clean the disc. Then apply the dye penetrant oil, which is a mixture of light penetrating oil and dye. After allowing time for the dye-penetrant oil to be drawn into surface cracks, wipe the excess oil off with a clean cloth. Then apply a light mist of a dye-penetrant surface cleaner on a cloth, and use this cloth to clean off the disc. Only the dye and the cracks will remain. Now, coat the surface of the disc with a developer, which is a substance that draws the dye back out of the cracks. Any cracks or flaws that are present show up in the developer. Also check the disc for steam cutting. If steam cutting is severe enough to allow leakage, you'll have to replace the disc. But if the damage is relatively minor, you can often restore the surfaces by lapping them. You'll need to follow the appropriate lapping method for the shape of the disc. If the damage isn't severe, you can probably restore the surface of the seat by lapping. As with the disc, you must use the appropriate lapping method for the shape of the part. When you're done lapping, clean all traces of lapping compound off the valve seat and all other internal surfaces of the valve. Then wipe any remaining residue off with a clean cloth. Now, use a light or bluing to inspect the clean seat for any nicks or uneven spots. If you find such imperfections, you'll need to repeat the lapping process until the surface is smooth and even. A valve seat may, however, be so severely damaged that you can't restore its surface by lapping. If the seat is a permanent part of the valve body, you can often use a reseating tool that's specifically designed to restore the damaged surface, or, as in this case, you can mount the valve in a lathe and remachine the seat. However, keep in mind that extensive maintenance on a valve seat may also affect other valve components and valve specifications, such as the lift. Next, check the adjusting rings for nicks, cracks, damaged threads, and steam cutting. Inspect them carefully, because any damage might cause them to fail when the valve is returned to service. Damaged adjusting rings should always be replaced. It's also important to check the straightness of the valve stem, because a bent stem is a common cause of valve malfunctions. A bent stem can prevent a valve from opening, or it can keep an open valve from reseating properly when system pressure returns to normal. Two common causes of bent valve stems are careless handling and improper gagging. Gagging is the act of attaching a device called a gag to a safety valve to keep the valve from opening. Gagging is usually a preparation for the testing that's done before a reassembled valve is returned to service. Proper gagging procedures are covered in the part of this topic that's entitled Reassembly and Testing. A common way to test a stem for straightness is to take a runout reading with a dial indicator that's mounted on a magnetic base. With the stem set up on a pair of V-blocks, place the dial indicator beside the stem and secure the dial indicator's base in position. Next, press the stem of the dial indicator against the surface of the valve stem until the dial indicator's stem retracts about 1/4 of its length. Set the dial indicator to 0 to provide a reliable reference point for the reading. Rotate the valve stem slowly while you watch the dial. Be careful not to bump the valve stem or the dial indicator. Compare the maximum change in the reading on the dial indicator with the specifications given by the manufacturer. If the runout is within the specifications, you can reinstall the valve stem. But if it isn't within the specifications, this indicates there's an irregularity in the shape or the straightness of the valve stem, and you must replace it. Also inspect the valve stem carefully for cracks and other signs of damage. The end of the stem that fits into the disc must be smooth and round, because it acts like a ball and socket joint inside the disc, so that the disc can align itself properly with the valve seat without damaging the stem. Flat spots on the disc end of the stem can cause uneven contact and unwanted friction between the stem and the disc. If either the stem or the disc is replaced or has any flat spots, you must lap the two parts together, This lapping process is called grinding in. Apply a thin layer of abrasive compound to the end of the stem and use a rotary motion to grind the stem into the disc. The grinding in continues until smooth, even contact is obtained between the stem and the disc. After a safety valve has been disassembled and its internal components have been inspected, the valve must be properly reassembled and tested before it's returned to service. The valve reassembly procedure is basically the reverse of the disassembly procedure, but there are a few tasks specifically associated with reassembly that you should be aware of. One of the first steps in safety valve reassembly is making sure that you have all the correct replacement parts and that the parts are in perfect condition. Lubrication is also an important part of reassembling a safety valve. You should follow the valve manufacturer's specifications for the exact type of lubricant and the method you should use to apply it. Typically, an anti-seizing compound is used to lubricate threaded surfaces so they won't stick together or seize as a result of temperature changes during valve operation. Also, during reassembly, it's absolutely critical that the disc and the valve seat make perfect contact so steam can't leak through the valve. Once you've completely reassembled a safety valve, you must test it to make sure that it's working properly before you return it to service. As with all other aspects of safety valve maintenance, you must follow your facility's procedures or the manufacturer's instructions for the specific valve that you're testing. But we can cover some general concerns that apply to most valve testing situations. Before you can test the valve, you must reinstall it. Take the appropriate safety precautions and follow your facility's procedures to make sure that the installation is done correctly, so you prevent leakage and other problems. Next, prepare to perform the necessary tests. An important preparation for many testing procedures is gagging the valve. Gagging involves installing a device called a gag that keeps the safety valve from opening during testing. We'll look at a typical procedure for installing a gag on a 2-ring Hudling chamber safety valve. The valve's release lever and the protective cap have been removed so the top of the valve stem is exposed. Now, align the stem of the gag properly with the valve stem. Then, attach the jaws of the gag firmly to the yoke to prevent the gag from slipping. Finally, tighten the gag finger tight only. Never use a wrench on a gag. Gagging a valve improperly can be disastrous. Damaged valve parts or serious injuries can result if a gag were to slip and the valve open unexpectedly. So it pays to keep in mind some basic safety tips about gagging. Never apply a gag to a cold valve that will be heated. The valve stem expands considerably as temperature increases, and if the stem isn't free to expand, it will be bent. Never leave a gag on a safety valve during normal system operation, because a gag makes a valve inoperative, and the system or equipment that the valve is installed on will be unprotected. Finally, many plant systems contain several safety valves. When you test the popping pressure of any of these valves, you must gag the valves that are set to open at a lower pressure than the valve that's being tested. For example, assume that a system contains these 3 safety valves. Valve A is set to open at 1400 psi. Valve B at 1450 psi. And valve C at 1500 psi. If you're going to test valve C, you must gag valves A and B, because the popping pressures of A and B will be exceeded during the test of valve C. Safety valve testing typically includes testing popping pressure. Popping pressure can be tested either by raising system pressure or by using an auxiliary device such as a hydraulic jack to lift the stem. If you use system pressure to test the valve, you should first lift the valve by hand to warm it. This helps ensure that the metal parts of the valve are at the same temperature before you start testing the valve to check its popping pressure. The parts will then expand and contract at the same rate during the test. In any case, when you're testing popping pressure, you're checking whether the valve opens when it's supposed to. If it opens too soon or too late in relation to the valve set point, you must make adjustments. For this huddling chamber safety valve, you make set point adjustments by turning the compression screw. But before you can do that, you must lower the pressure so that there's no chance of the valves opening accidentally while you're working on it. You must also break the lock nut free. If you try to turn the compression screw without loosening the lock nut, you'll probably damage the screw. Which way you should turn the screw depends on whether the valve is opening too soon or not soon enough. For example, if the valve is opening too soon, you should tighten the compression screw by turning it clockwise to increase tension on the spring. On the other hand, if the valve is opening too late, you should back the screw off a bit by turning it counterclockwise to relieve some of the tension on the spring. After you've adjusted the compression screw, test the valve again to see if it's been set properly. Usually, you need to make several adjustments and tests to fine-tune the set point of the valve. If testing indicates that blowdown has been changed, you'll need to readjust it. To make blowdown adjustments of this huddling chamber safety valve, you must raise or lower the adjusting rings until the blowdown is within specifications. Safety valves may also be affected by hydrostatic testing that's done on the system or equipment that the valves protect. A hydrostatic or hydro test is done to determine whether or not the system can tolerate excessively high pressure in case of an emergency. It also helps you detect leaks. Hydro tests are often performed at system operating pressure and below safety valve set pressure. But in some cases, during hydro testing, system pressure is raised above the normal popping pressure of the safety valves in the system. Then, gags must be installed on the valves before the hydro test is begun. If the gag on a safety valve is properly aligned and tightened, the valve won't leak during hydrostatic testing. But if the gag isn't installed properly, the valve will lift slightly during the test and sizzle. If this occurs, you should reduce system pressure until the valve closes. Then you should adjust the installation of the gag. Trying to pinch off leakage by tightening the gag without lowering the pressure could damage valve parts. After you complete a hydrostatic test, you should remove the gag when system pressure has been reduced to 85 to 90% of the valve's set pressure. Never leave a gag on a valve during normal system operation, because a gag makes a valve inoperative and leaves the system or equipment that the valve's installed on without the necessary protection from excess pressure buildups.